Welcome back. So, what we'll now continue because we have talked about now the dynamics and mechanics, and then simplified linearized model to analyze the design procedure. Um Now, what we would important thing to note here is that the whole turbine unit is essentially uh, responds to those different kind of loads, whether it's a static or dynamic or those kind of loads do arise during operation. So what one has to do, either it's a, it's a clear example of a coupled aeroelastic problem or fluid structure interaction problem. So one way to look at the complete design is that, these days the numerical techniques are quite evolved. Later on we'll quickly touch about the CFD part of it. So one can use complete numerical approach uh, where you can have that whole geometry can be totally solved through simulations, which could be fluid simulation alone, which is a CFD simulation. Then you can get all the aerodynamic forces, and then you can pass those forces to the structural solution and find out the structural responses. There are standalone ways. So the for flow simulation, one can use completely CFD. Then from here you estimate all loads. Then you can do structural analysis and find out the solution which can be used for the design purposes. Now, this is more like an applying numerical tool. So alternative to that we have discussed in details, the linearized simplified model, which is essentially the full flapping equation models incorporating different interacting effects and components. So one can use those simplified models, which are quite handy to get you initial design data. And then once you get the initial design data, then you can apply your numerical tools and then get complete picture or complete analysis of it. Then go for final fabrications and prototype testing. Now, regarding that complete CFD or full simulation of the flow simulations or for aerodynamic simulation, that we'll talk about the CFD and all this later on. Now, coming to the structural analysis, there are, different ways to get the structural response. So, already you can see that, wind turbines are complex structure. So it is necessary to determine various aspects of the response, such as stresses within the structure, deflection, natural frequency. Obviously, you can use mathematical model to find out that. There are also mathematical relations that can be used to describe the behavior of those real systems. Models can vary widely depending on the complexity incorporated in that physical model. Typical application for mechanical models in wind turbine design use simple model for control, then model which is sufficient for illustration. Then you can have detailed model for investigating fatigue, deflection, response. Then model for determining natural frequency of component or complete system. Okay. So like the linearized hinge sprint model that or hinge sprint dynamic model that we have discussed, that can be useful for elucidating the first order response of wind turbine rotor to a range of input condition. However, it is not that extremely useful in those situations where important aspect of the response would not become apparent using the such simplified. So obviously these are simplified situation. So to overcome that kind of situation, one has to use some specialized nonlinear models to investigate the dynamics of the complete turbine system, such as tip flaps, blades, pitch linkage, gear, trains. So yes, I mean, single simplified model cannot do that kind of analysis, and that is what we are talking about numerical tool or complete numerical tool, which can be handy to estimate the complete picture of the system. So one can do slightly segregated ways, like you do the load calculations or wind load calculations through or aerodynamic load calculation through CFD, and then use those loads for the structural responses, or can have a coupled system, complete aeroelastic behavioral, but which is really complicated, even with the numerical powers, computational resources that we have today. Still, it's an quite challenging for complete turbine system to have it. But component wise, yes, it can be done, and probably it would be good idea to look at that way. So when we come to the structural response, so there are, I mean, structural analysis can be done using different ways. I mean, the best way to do that using complete finite element method. So that means you will have the whole geometries done gridding and then run those finite element for structural responses and things like that. Or one can use lumped parameter method. Okay. So in lumped parameter is one in which a non-uniform body is considered to be made of a relatively small number of bodies, which can be simply characterized. So this characterization may consist of as little as the mass of the body, or it may include other parameters as well, such as stiffness. For example, the drivetrain of a wind turbine in reality consists of a number of rotating components such as rotor itself, shaft, gear, generator rotor. So to modeling a drivetrain, it is common to characterize as a few lumped inertias and stiffness. So this is what, so that means you can kind of consider different components and use their stiffness or inertia as a lumped parameter and use that in a simplified analysis. So that is obviously cost effective compared to finite element method, but it is better than simplified linearized system. Okay. Now we can have modal analysis. So modal analysis again is a method which is used to solve the equation of motion in multiple degrees of freedom vibrating system. So this particular approach allows coupled equation of motion to be transformed into an uncoupled modal equation, which can be solved separately then. And then finally, the solution from each modal equation can be superimposed or superposition to give the complete result. So this is quite useful for linear systems with classical damping. Okay. Or one can use multi-body analysis. So in multi-body analysis, it is the modeling approach of the motion of a mechanical system which comprising more than one component of a body. Okay. So bodies are distinguishable subdivisions of the larger structure which are relatively uniform with themselves. I mean, for example, wind turbine include tapered or twisted beam, various other tapered parts, couplings, generator gears. The bodies may move in a variety of ways with respect to each other. Bodies could be rigid or flexible. Bodies are joined together by links, which may incorporate certain constants. So the multi-body method involves the creation of dynamical equation involving the various bodies at their constant. So this is a again involved analysis which is done in classical mechanics, which is the extended version of Newton's law of motion, but it has become progressively more complex and inclusive with time. Okay, so this multi-body analysis is quite popular. I mean, obviously, if you see that, I mean, either you can have linearized system or simple linearized model to carry out the analysis, and or you can have slightly more complicated like lumped parameter method where you couple together different components, for example, all the and consider them as one big unit and having some inertias and stiffness and all this, you can solve that. You can do modal analysis, which is multi degrees of freedom vibration analysis, and then finally once you get those modes, you can kind of add them together to get final solution. You can do multi-body analysis, and APM is the kind of the or so this is where you get the structural analysis, and for wind loads and all these you can use the complete CFD or a coupled aeroelastic problem using CFD and structural system. Okay. Now, just quickly touch upon there are electrical aspects also of wind turbine. For example, the electricity is kind of essentially from the wind turbines you generate the electricity. So the electrical aspect is also very important. I mean, there are different components or electrical issues which are significant in the wind energy system. Like you have power generation. So those are generators for electric converters. Then you have interconnection and distribution. So you have power cables, have switch gears, circuit breakers, transformers, power quality. Then you have control. So sensors, controller, yaw or pitch motors, solenoids. Then you have site monitoring, data measurement, and recording, data analysis, storage, where you need batteries, rectifiers, inverters, lightning protection. You have grounding, lightning rods, safe paths. Then you have in loads, which is lighting, uh, heating, and motors. Okay, so these are the, I mean, obviously you have this electrical aspect, these different aspects of the electrical system like power generation to interconnections, control, site monitoring, storage, lighting protection. So, I mean, one has to also look at it. I mean, truly speaking, this whole wind energy system design, integration, all this, it's a multidisciplinary system. It is not only understanding of the aerodynamics, force, and all this required. Then you have a structural responses. Then you have the electrical part, which are, I mean, you have to have a basic concept of the electrical power, then power transformers, then electrical machines, power converters, then variable speed wind turbines, any other ancillary auxiliary systems which are associated with that. So one has to have a quite clarity about this aspect of it as well. Similarly, I mean, this is one aspect of the now. So electrical side of it that one has to know. Similarly, one has to understand the wind turbine materials and components because there would be material fatigue because the turbine is exposed to the dynamic loading. So now the materials typically used in wind turbines, I mean, different, like if you look at blades, these are composite. Mm, I mean, these are material. You have subcategory as fibers, carbon fibers, wood laminates, polyester resins, epoxies. Then hub, you have steel. Then gearbox, you have steel, where you can have various alloys, lubricants. Then you have generator, steel, copper, which is rare earth based permanent magnets. Then mechanical equipment, which is again steel. Then you have nacelle cover, which could be composites like fiberglass. Then you have tower, which can use steel. Then you have foundation, which could be steel, concrete. Then you have electrical control systems, all these which would be copper, silicon. So you can see there are different materials which are often used in the different components of this. Also, you have different machine elements like shaft, couplings, bearings. You need gears. Uh, all these are the different kind of gears, gear loading. All these can be also estimated. Then you have principal wind turbine components, which are rotor. So rotor will include blades, aerodynamic control surface, hub. Then the blade, you have to consider design consideration from the aerodynamic concept. Then, I mean, aerodynamics performance, then structural strength. Obviously, that's how you do the design, and then finally get the blade shapes and all these things. You find out the blade, I mean, number of blades, airfoil, solidity, all these things. Then obviously overall system structure stability, and those things are there. Now, I mean, wind turbine, essentially the design procedure includes all of this. Okay. So one has to determine the application, review, I mean, the whole design procedure, determine the application, review previous experience, select topology, estimate primary loads, develop tentative design, predict performance, evaluate design, estimate cost, refine design, build prototype, test prototype, and do that. So all these are part of the wind turbine design procedure. Then you have the turbine topologies that one has to find out, technical specs, certification, calculate, you have to calculate the wind turbine loads, load scaling relations, power curve predictions. Then obviously one can have, I mean, computational code to estimate all these. Then finally, design evaluation. So finally, you have design evaluation, where you can prepare the wind input, model the turbine, perform a simulation to obtain loads, convert, and assess the damage. So wind turbine then One can do component testing, and all these things can be done. So after doing the turbine component testing, now one has to understand the control of the wind turbine. So what we have in the control is you have passive control by mechanical design. So in the passive control, you make this kind of a modification to the geometry, or you can have active control by using sensor actuator system, where you have a digital controller, power amplifier, actuators, turbine, and sensor, and use those to control the system. So when you look at the sensor, you have, sensors are used to for different, used in different components to sense the generator speed, rotor speed, wind speed, yaw rate, temperature of the gearbox oil, generator winding, ambient air, blade pitch, blade azimuth, yaw angle, grid power, current, voltage, grid frequency, start stop acceleration, gearbox vibration, shaft torque, and environment, whether icing, humidity, and all these things. So now, and there are actuators, which are generators, motors, which control pitch and yaw, linear rotors, magnet switches. You have hydraulic powers and pistons, resistance, heaters, fans, brakes, and all these things. Now, how the control architecture look like. You have a wind farm operator, you start up, then online control, component wise, then shutdown. So basically dynamic component controllers. If an emergency shutdown, fault monitoring, so it comes back. So usually supervisory control is on high level for turbine appearing status, and dynamic control is on low level. So dynamic control is low level, and that is, for example, torque, pitch, power, etc. And supervisory control is on high level for turbine operating status. Okay. Now, how do we control of a variable speed turbine? Actually, we have main actuator for speed control, that is a blade pitch and generator torque. Here is a rotation speed as a function of wind speed, and you can have it is broken down to different segments: cut-in speed, rated speed, shutdown speed, and then rated power. So with the problems that wind speed on rotor disc cannot be perfectly known, what is the maximum power production and power coefficient that can be obtained? So we have power, which is basically area into piston velocity into coefficient of power. So these are the tip speed ratio, collective bed pitch, and all this we have known. And then, so what we can find out that Q generation in the generator torque is in equilibrium with the aerodynamic. Then region 2A, where lambda is fixed to that, so beta is maximized, and CP could be function of this. In region 2B, which is subrated, lambda is lambda star, beta is beta star, CP is CP star. Region 2C and 3, lambda is again fixed to this, and beta regulates power, is a maximum power. So this is how you can get some kind of an control. Now, when we talk, the Q generator can be controlled directly and should contact aerodynamic torque when we know the given inertia. So aerodynamic, the torque is the power of aerodynamic power by rotational speed. So if you put this expression back, and then you can find out what would be the then how to choose the Q generator when only omega is measured. So idea is to find the function of Q generator that brings turbine to an optimal tip speed ratio, intuitively setting Q generation, and then we can use the basic equation to find out that. That's how you can find that how one can control this whole system like that. So apart from the control aspect, there are other things like uh, wind energy application. Okay, so that means one can look at the distributed generation, hybrid power system, hybrid offshore wind energy. So those are there. Then one has to look at wind energy system economics. So that is another important part because it's not only the design and operation, all this. So system economics is another aspect one has to look at it. And also one has to look at the wind energy mm, systems where environmental aspects and impacts. So that is another thing. So not only the designing a system, also looking at their environmental impact and their aspect also one has to be considered. So when you try to design the complete system, um, uh, one would like to have a complete picture of the overall system, starting from site selection to the design procedure and their subsequent impact to be in place. So these are the different aspects that one has to take into consideration in wind energy application. Now, in the we'll talk about some CFD aspect and alternative concept.